allyl hydrogen bright enough to cause sulfur cross-linking. At the same time, this generation of sulfurating agent during the course of vulcanization and its interaction with the right repeating unit or the functionality of the backbone demands that the sulfurating agent should be of right chemical activity. And this requirement is translated the form of using a higher quantity of a fast accelerator. In this case, it is TMTD. And that is further supported by the mercaptan benzothioazole. Right? And even though the carbon black in this recipe uses N330, that is not the filler for butyl rubber in number of products. Normally, it is a blend of N660 or N770 or N770 and N550. So you will have N550, N660 or N550, N770. Right? So the idea is, as we said in the previous class, FPF it combines the right particle size and the structure. Structure is required for reinforcement. And the FPF particle size enables good processing. And the air holding product, namely the inner tube, make a note, tire inner tube. So the processing is extrusion. So for extrusion, you use the right filler. And in a compound, rubber compound, next only to the rubber, it is a filler that is consumed in a larger percentage. So that way, filler has a definite role. All right. So that is the first qualification of this recipe. And secondly, the inner tube formulation has to be flexible. It should be soft, flexible, soft, and hardness is just about 50. And usually it is formulated with the filler and process oil. And the process oil, otherwise we call it as a flexibilizer, because beyond a certain pH, it qualifies as a plasticizer. So the plasticizer for butyl rubber is naphthenic. All right, and butyl inner tube, after certain life cycle, the scrap or the process scrap is again used, namely in the form of a butyl recline. Butyl recline. You must have studied the reclaimed rubber in the rubber chemistry. So butyl recline also forms a part of a inner tube formulation. So these are the additional features we'll have to consider in butyl rubber formulation. So coming back to this recipe, just look at the cure temperature. It is at 170, that too for 20 minutes. And if you go back to the natural rubber, the cure temperature is just 150. And cure time is okay, 30 minutes. All right. Whereas a butyl rubber, it can support a higher temperature. right? What does it mean? For products that demand high temperature application, butyl rubber, and it has a specific role. So there is a product called curing air bladder. Make a note, curing air bladder, and that is used in tire manufacture. Curing air bladder used in tire manufacture. This curing air bladder, as the term implies, it helps in the tire curing, and it is either a high pressure steam, usually high pressure steam. So the bladder holds a high pressure steam, and this high pressure steam, the temperature is in excess of 100 degree, and this has to be repeatedly used. So the air bladder is another potential application. Why potential? It is being used. Butyl, and this recipe tells you the possibility of curing butyl rubber at a higher temperature. Okay. All right, and so that is about the butyl rubber. Butyl rubber is also used for used in electrical insulation, and why? Because the almost close to 97 to 98% of the backbone is the saturated, and saturated free from any active functional group that may interfere with the electrical insulation. So, so that way butyl rubber electrical insulation. And prior to silicone rubber, the butyl rubber was used in pharmaceutical application. That is for pharmaceutical as a stopper, because it can give the best balance of flexibility as well as chemical inertness to biological fluid. Okay, so that way butyl rubber, even though it is a very sluggish, high damping, and practically no resilience, which is in contrast to the rubberiness that we know. Rubberiness means what? Should be resilient. But a butyl rubber, there is no resilience at room temperature. Even then, its TG is sub-zero. It is about minus 50 degree. And it is also amorphous. And it can also be cross-linked with the sulfur. So it rightly qualifies as a rubber. Okay. So this background is important. Right. Let us move on to another interesting homopolymer, which is often used in place of NR and SBR, right? And between NR, SBR, EPDM, and nitrile rubber, there is a gap. Okay? So we will see what that gap is. Right? So that gap is effectively filled by chlorophyll. So on the one hand, what we have? NR, SBR, EPDM, and possibly we can add butyl rubber. So they are all hydrocarbon, and we don't use them for contact with the organic fluid or this thing solvent application or the that is medium or media that can disturb the backbone. So hydrocarbon. On the other hand, you have a nitrile rubber, which is a solvent resistant rubber. So in between that, we'll have to fill the gap, right? And chloroprene rubber, polychloropyrene rubber is a best candidate. All right, and you must have studied this rubber because of the chlorine that is present responds to metal oxide. And last class, referring to a particular question and answer part, we discussed the chloroprene. All right. Well, friends, so the chloroprene rubber, why it is special? It combines, listen very carefully, it combines a best set of mechanical properties known for NR. One. And the moderate weather resistance, that is weather resistance moderate. Weather resistance is known for EPDM and the butane. And chloroprene, it's just about a moderate, but definitely better than NR or a SDR. So that way, weather resistance. And since it contains the uncross-linked chlorine in the main chain, it adds to the polarity, so it can give you moderate solvent resistance and the grease resistance. So that is the third speciality. The fourth speciality is the chlorine that is present. It can control the flammability of the backbone. So meaning for flammability, the hydrocarbon has to react with the oxygen. And chlorine and oxygen, they compare in respect of the electronegativity. So the chlorine that is present does not promote a flaming. So that way you have a flame resistance. And the fifth this thing attribute of chloroprene is the its resilience at an elevated temperature. Right? That is the fifth, which NR cannot offer. Elevated temperature, chloroprene, it gives you resilience. All right, that is the fifth attribute. And sixth attribute was say it is it can be polymerized. This is an emulsion polymer, and you can vary the way the repeating units are aggregated or catenation. So the repeating units are added and you get a polymer. You can have a completely crystalline and a completely amorphous. And okay. And another interesting aspect is what is a modifier. So in this case, it is a W type. So modifier is a W type here. You also have a neoprene sulfur modifier. This one is a mercaptan modifier. Neoprene mercaptan modifier. So the sulfur modified is a neoprene G, alphabet G. So neoprene G means it is peptizable, make a note. Neoprene G is a peptizable. And neoprene W, it does not respond to peptizing, one, and two, its molecular weight is already adjusted. Meaning, what is the not the molecular weight? Molecular weight that would correspond to the normal processing. So the viscosity is the 50. Listen very carefully. 50, right? So 50, is it a solution viscosity or anything else? So here we qualify the rubber viscosity. You may have studied that is the Mooney viscosity. Okay. I don't know if I have space to type that. Mooney viscosity. Sorry here. So you better note down that, and maybe in the chat I would add. Don't worry. So Mooney viscosity is about 50 at a particular test temperature. All that we will discuss. Okay, and this viscosity stabilized rubber is largely consumed for the molded rubber goods. For molded rubber goods, if we want to, if we choose chloroprene rubber, then we often go for a neoprene. I'm sorry, the Mercaptan modified. Neoprene W implies a trade name of a particular company. So don't worry about the trade name, which company, etc. Neoprene W means that is a trade name. Polychloroprene rubber. Okay. So you have this many positive features and that differentiates from the hydrocarbon rubber. But there are a couple of limitations with the chloroprene. Number one, the low temperature stiffening is rather unpredictable. In number of cases, low temperature stiffening is faster. Right? Low temperature stiffening, unlike NR or SBR or a butyl, even for the matter EPDM, you can give some guarantee that this product would would offer a modulus of a definite quantity. Whereas in case of chloroprene, you cannot, you simply cannot do that. Even though there are compounding procedure that would delay the low temperature stiffening, the compounder is vary about chloroprene rubber for low temperature. Of course, it has a low TG, no question about it, but it cannot be. Occasionally, it can give a high modulus. Low temperature stiffening is revealed the form of a unusually high modulus. Modulus means low flexibility, and in fact, we use rubber for the flexibility. So that is one word of caution. Another concern is in number of cases it is beneficial. In certain cases it is a concern. Meaning chloroprene rubber, you may have studied, it has a specific gravity of 1.23. So the other hydrocarbon rubber specific gravity is less than 1. And in fact, EPDM, we continue to use in very large quantity just because of its low specific gravity, about 0.82, 0.84. So that is a specific gravity. Whereas chloroprene rubber specific gravity is 1.23. Okay, what does it mean? For a given volume, the product mass would be higher. All right, and so that may limit filler addition. So the filler often uses a carbon black or some mineral fillers like China clay, calcium carbonate, or some of the silicates, silica in certain cases. All this have a higher specific gravity. So the rubber is already heavy, and you cannot add a heavy filler. Okay, unlike EPDM. So this is the second limitation. And third one, not exactly a limitation, but that is the inherent quality of a chloroprene rubber. Namely, it can give you what is termed a marching modulus. Okay, it can give you marching modulus. So anyway, I will take you to another page to describe what marching modulus means. Let us complete this chloroprene discussion. So in this test recipe, 550 is the 550. Often it is the SRF. I am using the term SRF, semi-reinforcing furnace. SRF stands for semi-reinforcing furnace. So that is under 700 series. N700. SRF GPF. Right? We don't use even N550. Alright? N330 for a chloroprene, very rare, very rare. Okay? And so chloroprene rubber Where do we use? Wherever weather resistance and little more solvent resistance and best set of mechanical properties, as in the case of civil construction. Civil construction bearings, bridge bearings, earthquake protection bearings, rubber bearings, bushers, okay, and certain diaphragms. NR and chloroprene are so, chloroprene is also used for such application. Okay. And those application they don't require abrasion resistance. N330 is for the abrasion resistance. That is what we saw last class. All right. So friends, this is what is the pure cross-linking mechanism, that is we'll have to generate a cross-linkable site in the one chain and another chain, so that we can insert some bridges. Unlike the sulfurating agent, for chloroprene rubber, it is a metal oxide. Okay, so we often use zinc oxide and magnesium oxide in combination. Zinc oxide is a cross-linking agent, and magnesium oxide, what does it do? It causes this thing dehydrochlorination, and that acts as the acid acceptor. Okay, HCl acceptor, that is the magnesium oxide. Okay, and that also helps in maintaining a process safety. Magnesium oxide, process safety. Okay. Zinc oxide is a cross-linker. So we use the zinc oxide at the end in chloroprene rubber compounding. In all other rubber we discussed so far, including NBR, we add the zinc oxide in the beginning. That is the order of addition. Whereas in chloroprene rubber, we are strongly advised to use zinc oxide at the end, because that is a cross-linking agent. And what is not listed here is an organic accelerator, and we saw last class it is the ETU, ethylene thiourea. Ethylene thiourea. This ETU is almost removed from rubber compounding, because it is known as it is rat poison, and it is harmful for human consumption also. Right. And in its place, you have a thiazine. So what is the Cura accelerator? Activated thiazine. So this again contains some sulfur and nitrogen in certain functional groups. Okay, definitely not that ethylene thiourea type. Okay, so that is about this polychloroprene this thing, and polychloroprene rubber. In terms of as we see here, so look at because if we have chosen the polychloroprene rubber, we often come across products based on the hardness. In case of NR also, we saw the hardness specification, right? Here we have the hardness specification N550, 25, 50, 75. So the hardness is about 50, 65, 80. All right, and modulus also just about couple of units increasing. Tensile strength is almost maintained. Breaking elongation is the one parameter that is compromised. All right. So in terms of the strength in terms of modulus and tensile strength, it is just about 20 plus, 20 or 20, right? Even at a higher hardness. So what we lose is the elongation at break. All right. And in this, so we have seen this chloroprene rubber. So look at NR. So NR, what happens to the similar trend? So NR, we don't lose the elongation at 70 for the 75 hardness. It is 550, whereas for the chloroprene it is about 300 or 350. Okay, so what does it mean? NR can accept a higher filler, offer the higher hardness, at the same time maintain a good elongation. So high tensile and high elongation, these are the fundamental requirement. Listen very carefully. High tensile, high elongation, fundamental requirement for any rubber product. Okay? Because we use the rubber to store enormous elastic energy. Okay? Elastic energy. So compared to the NR, chloroprene 550 at 75, it is going to it will have a high specific gravity, compound specific gravity will be much higher. Whereas NR, you have it is about 1.1 or so, whereas chloroprene may be of 1.3 or 1.4. Okay? So that is one aspect, and one major limitation of NR is the high temperature application. You cannot use NR beyond 70 or 75 degree. Whereas chloroprene rubber, you can continuously use at 90 degree or 100 degree. So that gives you that whatever the benefits in using NR is almost nullified at a higher temperature. NR is a very poor candidate. And there are compounding techniques that can solve this thermal issues, compounding, but they are not so common. Okay? Now I take you to what we understand by the reversion and Plato, etc. Okay. Yes. And do you see the figure 2.1, friends? Hello? Hello? Figure 2.1.
Yes, sir.
தெரியுதா?
தெரியுது sir.
Yes. Well, so this is very important. In fact, we are just looking at a sigmoidal curve, an S-type. Okay, S-type curve, and we have two variable mentioned. One independent variable time and dependent variable torque. Okay. After cross-linking, so up to a particular point, cross-linking happens. So once the active cross-linkable sites are consumed, there is a secondary modification happen. Secondary modification. This modification, if it leads to breakage in the main chain or in the cross links, we end up with the phenomenon called a reversion. And in contrast to the reversion, if we continue to use this active site in the main chain beyond the optimum curing, so additional cross-links are formed. This additional cross-links will make the cross-linked rubber much more solid-like. So that causes a higher torque. Okay. So one is a reversion, another one is a additional cross-links. Additional cross-links are a certain main chain modification. Even in the absence of some cross-linking agent, so assisted by these cross-linking agents, byproducts, a certain main chain modification is happening. That is what we consider as the marching. Okay, marching modulus. What marching modulus? That very well goes with the rubber chloroprin. Polychloroprin rubber marching. And closely following chloroprin is the SBR. Marching SBR. In certain nitrile rubber composition, we come across marching modulus. Right? In case of NR, butyl, NR, butyl. In case of NR, you may have studied the ENR. ENR is a epoxidized natural rubber. NR. Okay. NR and in number of majority. Okay. I'm not generalizing for 100%. Let us say about 90%. 90% of a compounding recipe that we come across or in terms of volume we consume, it may either be a reversion or a little tendency towards Plato. Plato is what? That is the equilibrium modulus. Equilibrium meaning for a certain number of new crosslinks formed, certain crosslinks are broken. Okay, they are getting cleaved. Okay, so what does it mean? We are able to maintain the viscoelasticity even at a higher temperature. So reversion is a definite limiting factor in case of NR butyl rubber. Okay, you follow? And every effort is taken. The compounder looks at pushing the reversion to Plato. So what is the Plato? Equilibrium modulus. Equilibrium modulus. And in case of natural rubber, there are chemical additives that can minimize the reversion. They are called anti-reversion agents. Anti-reversion agents. And I remember I told you the anti-reversion agents being promoted for NR is perhaps the only ingredient that is water soluble. Okay, only ingredient that is water soluble. What does it mean? that can interfere or that can suppress the cross links from getting broken. And there are reaction mechanisms studied and literature are available. So the point here is chloroprene rubber, in the absence of, listen very carefully, in the absence of organic accelerator may give you marching modulus. This marching modulus is not so desirable, okay? Because the modulus at elevated temperature is unpredictable, and modulus knowledge of modulus and size of the geometry of the product, right? Modulus is a material parameter, and product geometry, it gives you what is the how we have distributed the volume of the rubber into product geometry. Okay, that is the size and the shape. That is the geometry. Okay, these two, geometry and the modulus, right? They translate as a product stiffness. Product stiffness. So geometry and the material character from the stiffness. Okay. So, however much we study and control the product geometry, if the material is not able to maintain a particular modulus at an elevated temperature, why elevated temperature? Even low temperature stiffening is also a problem. You follow? Low temperature stiffening. So, and so stiffness is an important variable. Another one is the damping coefficient or a damping ratio. Damping ratio is the normally preferred. It's the damping ratio. So stiffness and the damping ratio, they are considered vital inputs of rubber products for rubber seal, isolators, vibration, isolators, rubber seal, rubber bearing, rubber bushes, right? And we cannot extend it to tire or a conveyor belt or a diaphragm, because in case of tire, conveyor belt or a diaphragm, they are all reinforced rubber products. Reinforced rubber products. And the last class we saw carcass. The carcass is a part of a tire and a conveyor belt. And it is just not the rubber, it is a reinforcement that can alter the stiffness of such products. Whereas plain products like isolators, vibration, isolators, bushes, and bridge bearings, right? And dust covers, gaiters, engine mounts. Okay, these are all rubber based. So just a rubber and a rubber compound and the filler related issues. Okay? So that way, for such products, what are the parameters? Stiffness and the damping. Stiffness and damping. Okay? Just take a couple of minutes break here because there has to be some room cleaning. I'll stop recording and stay on the line. We will join. Okay.